Okay, good evening. So today we're going to start talking about Windows. And before we will continue with Windows forensics, we need to discuss first details about hard drives. And there are few different types of hard drives, but we're not going to talk about types. We're going to talk about technologies. So first technology, it's magnetic hard drive that has platters, moving platters inside. So basically, it's like a box, and we have platters, just like DVD platters, stuck on a spin. And we have a handle for each of this platter that it's called arm that do reads and writes on these platters. So these platters rotate and arm is moving. And this way, information can be recorded, erased, or read it from the platters. And before we move forward, we need to know what's going on the platter itself. So platter has tracks. Basically, like if we look at the vinyl, it looks exactly like vinyl, except it's a paramagnetic material. So the data gets magnetized instead of uh, like when vinyl physically get into the vinyl. So each of these tracks can be divided in multiple sectors, like small, tiny sectors. And those sectors will be united into clusters. You have to remember that sector starts always from zero and counting from zero. The size of cluster will vary depends on the file system we will use. So first you need to remember sectors. Then is clusters. And then we're going to have tracks. So what happened when we're trying to record the data? The disk is spinning, the arm is moving, and it starts recording the data continuously on the disk. And when it's recorded the data, it will put information about recorded clusters. And yes, not about sectors, about clusters, because cluster would be the the smallest readable um, readable particle. I'm sorry, I forgot the word. So with that saying, we have to remember that information in these clusters not always continuous. Sometimes it can get fragmented and written in all different places of this drive, and not only on a single platter. It can be on different platters, and those platters have tracks from the both sides. So back in the days when our computers, and some of you still use computers with hard drives, had to be defragmented. Those drives had to be defragmented. That's a process when files, Windows will move those files to clusters to be next to each other, basically. And with this, it would be speed up the process of reading files and will increase the effectiveness of the work of the system. So, with that saying, we're talking now about FAT systems because that's what we used with hard drives back in the 90s, right? Windows came up with file allocation table. And how file allocation table work? Okay, I'm going to erase right now my perfect, beautiful uh, hard drive that I just drew. I need to resize it. Yeah, good enough. Okay, so we have file allocation table where information about each individual file chunk will be written into the table. And for example, this our clusters numbers. And we will get assigned to each cluster what type of information, what is we keeping there. So for example, we have this text dot txt, text dot txt, and here we have something else. And for example, we have text dot txt here. So as you can see, they're not continuous. And with the defragmentation, this would be moved here to make for the hand not to go all over the disk or for the system try to search all over the all platters for the next chunk of files. So the reading would be very fast compared if files get defragmented. But that's the reason this system called FAT, because it used file allocation table. The table that tells where exactly each file located on the drive. Now, if we delete the file from the drive, what do we do? Do we delete this file? No, this file will not disappear from the from the disk. It will disappear from the file system only, from the file allocation table. So that means this pointer no longer points to this file. However, this cluster still will be occupied with this file. How it works for the forensics? Well, if you need to restore deleted files, it would be very easy. You just use some simple forensic tools, open source tools or FTK, and you simply restore each file. And it doesn't matter if a file allocation table doesn't have any more pointers to those files. They are still there, they still exist. Now, let's talk about solid state drives. So with solid state drives, we have not little bit, forgive me, completely different technology. So when we compare hard drive and solid state drive next to each other, we see two metal boxes. Well, at least back in time. Now, solid state drives look a lot different than they used to. They became a lot smaller. But back in times, and still now, you can find solid state drives that from outside look exactly as hard drives. Solid state drives don't have any moving parts in them. Solid state drives have NAND chips. So basically, it's like a silicon chip on the circuit board, and not one, few of them. And let's talk how this chip works. So you will have a cell as the smallest unit. Okay, I'm using eraser to draw. So cell as the smallest unit of NAND chip, and it's called NAND cell. This NAND cell can have two positions, 0 and 1. And quick question, I want someone to answer. How do you think that if we have information in the cell, written in the cell, if our cell is not empty, would it be 0 or 1?
1.
Incorrect. So when we talk about regular hard drive, that's perfectly normal. That's what everybody makes mistake with. When we talk about regular hard drives with the spinning, that's exactly how it would be. When you're writing information into a sector, you will put 1 in this sector as a bit of information and 0 as nothing, right? So with NAND, it's different. NAND cells, they are pre-charged. And depending on the NAND cells, because there are different NAND cells now, they're more advanced, and we're going to talk about this in a moment. This condition of this cell will change. The amount of charge will change. So when this cell losing its charge, it's when it's receiving information written inside. So 0 is actually when information in the cell, written in the cell. So newer NAND cells, they can keep up to 3 bits of data at the time. And they can have conditions such as, oops, I was supposed to write 1, 1. They have conditions such as 1, 1, 1. Oh, I don't like pencil, too small. 0, 0, 0. And anything between them. So which is 0, 0, 1, 0, 1, 1, and 3 ones we already have. I sort of didn't put enough space for that. Oh, so actually there are more of them. So it can be 1, 0, 0, 1, 1, 0. It should be 8, so it's 6. What am I missing? 0, 1, 0. Guys, help me. What am I missing here?
101.
1, 0, 1. Yes. So that's different conditions that can be written into the cell depending on how much charge the cell is losing. So we can encode up to 3 bits of data in each cell. And what it gives us, simple explanation you will find with the video on YouTube that I have on link to the canvas. But current information requires us to save faster and with taking less capacity, and that's what SSD drives offering to us. So they have no moving parts. That means they are very reliable. They have no moving parts and no rotating disks and no ARM to read. which make it faster, but it also uh, contains something that we need to learn about, and we're going to talk about this right in a second after I finish explaining. So the way it reads information, it's a lot faster that reads or writes information. It's a lot faster than when we were using normal hard drives. And so cell, it would be the smallest uh, unit of the hard drive, of SSD drive, but that's not the smallest readable unit, and is not the smallest readable unit. And now we're going to talk about how these cells will be united into V, which is vertical, and it's string. It's called string. So it's called V string because it's vertical string. Then each vertical string will be united into the page. And page will be your smallest readable or writable unit. Now, we have this bunch of pages and bunch of strings. So we have a sort of row of strings and pages, right? Like this, just. But remember, they're 3D, so there are many of them. After this row, we have next row, and after that row, we have another row. And 6 rows will create a block. The block will be the smallest erasable unit. So when you're erasing information by blocks. When you're writing information into strings. My bad, pages.
What could make a block go bad?
Anything can make block go bad. But it's actually a really good point with this question. So if we have our information written in pages, and remember that information is not written continuously, right? It can be all over the basically entire chips. It doesn't even have to stay in the same chip. And I haven't finished how chip is formed. Basically, all these blocks will be put in different multiple layers and covered with the silicon, and that's what creates the chip. So when we're writing a file, this file can be all over SSD, in any of these chips, in any layer of the NAND. So if one block goes bad and you have the rest of information written in the good blocks, you might assume that some information will be lost. However, scientists came up with the idea that this information in blocks will be erased and rewritten in different blocks constantly. Like every time you power up SSD, the information will be changing from one state to another state. Let's think from forensic perspective. What type of challenges it would create to us? Think about last assignment that we just did, when you had to create hashes of your files. What is the hash? What hash provides you?
Would the hash change if it was moved?
Exactly. So hash provides the integrity of the file. That file have not been altered, right? So when forensic acquisition happens with SSD drives, at the moment when they acquire old data, they take hash of this drive. But it doesn't mean next time they will power up this drive, the hash would be the same. Even nobody did any changes to this drive. Because of the way that drive operates, it would constantly move the data within these blocks. So cells will not go bad, because if cells will contain the same data all over, like for long periods of time, it will go bad. So it needs to be erased and rewritten constantly in order to continue work. And back in 2010, Belkasov, they wrote their first article that named SSD drives destroy the evidence. And that's not the first and only challenge with SSD drives when it comes to forensics. So it will change the okay, we will move forward. I'm jumping right now. I'm gonna try to stay on so now you know the difference between two different drives, right? You know how these drives operate more or less. And with hard drive, all you have to remember, even if file was erased, if the sectors was not overwritten with different files, you can restore the data. However, when you're working with the SSD, when data erased, there are algorithm that called TRIM, T-R-I-M, that basically erases completely this data from the NAND. So it's not just erasing pointer from allocation table. It does erasing data completely. So if you try to restore, and I posted video to another person who shows exactly, and if you want to read my research, I wrote my capstone project on this. There is absolutely no way to restore the data that's been trimmed. But you would say, why would people use trim? Like, why it was even invented if it creates such as obstacles for forensic purposes? Without trim technology, information will still stay there, right? But allocation table would not know about this information being stored in these files. So these files will be keeping this data for long enough to go bad. So system doesn't want NAND cells to go bad. It needs to move this information. It needs to remove and replace this information with different one in order to work, to continue work, to be able to operate. So without trim, you're erasing data, but it stays there. You're erasing data, it stays there. So nothing can be written on top of this data. So when we're working with hard drive, if we erase the data, it can be overwritten. It can be sort of written on top, and then we cannot restore the file that was previously there in those clusters. With SSD, it works completely different. So trim is off, is not trimming. It doesn't matter if we even format the SSD drive. It's still gonna be there. So technology of trim is important for SSD actually to work and being able to operate. Just like defragmentation is really important for hard drives. Do I have to explain why it's big challenge now in forensics? Probably you understand that if data erases completely, that means there is no evidence to collect. NAND cells and SSD drives brought us different challenge. Uh, Even if it's erased, it cannot be, any data cannot be completely erased. So every SSD drive has a reserve capacity in order that when some blocks go bad, they sort of replace bad blocks with the reserve blocks. And remember, the information is constantly jumping back and forth and jumping around. So if accidentally some of the blocks with data got into a reserve capacity, it would never be able, like you would never be able to erase this data. So at the same time, you cannot restore deleted information from SSD drives, and you cannot completely forensically wipe it. Let's think of how would you destroy data from SSD drive if you want this drive to, like the data on this drive to be destroyed completely. Anybody?
Burn it. Incinerate it.
Well, apparently it's not that easy to burn. I personally
Hit it really, really hard.
Sorry?
You're gonna have to hit it really, really hard.
Also disagree. Well,
Didn't you
you
say
will break some chips, but it doesn't mean it's not gonna.
Would you rewrite over it or throw it in that biohazard trash can type idea?
Rewrite is a good idea, but
didn't you say if the block goes bad, then you lose that data?
I'm sorry. Can you please repeat?
You said that when the block goes bad, you lose that data. So is there a way to make the block go bad?
Yeah, there are ways. So honestly, in the high secrecy companies such as like military, they would not reuse those SSD drives. And as funny it is, if you will start researching how to destroy SSD drive, there is something that looks like a blender. You know, the blender you do smoothie in. You put NAND chips in this blender and you destroy it. And as a joke, we called it NAND smoothie. But if you want to, for example, you trying to sell your computer that has SSD in it, you would use forensic wiping tool that 7 times overwrites the data. So it would erase your data with stream, right? Then it will write down some random nonsense data, like bunch of zeros and ones that makes no sense. Then it will erase everything again with stream, and it will go over this process for 7 times. Takes a lot of time. Restoring data after that is impossible at all. So that's one of the ways to sort of destroy the data. In forensic world, SSD is a nightmare. And there is still, like, it's 2020 today, and it's first discovered in 2010. And believe it or not, there is still no technology to stop that from happening. I've been trying to use write blockers, and I thought write blockers would help SSD drive to stop from moving data every time we giving power to this SSD drive. No, it doesn't work because this technology actually inside of SSD drive is not controlled by operating system. So to keep evidence, the only way this SSD will keep evidence is when trim is off. And sometimes people don't know that their trim is off. However, Windows system comes with preset Windows trim operator on. So you don't have to even turn it on. It comes this way. And now all Linux distros and of course Mac OS come with the Dream on. So because what happened back in the days when they started mass producing SSD drives, people didn't want to purchase because they noticed that SSD drive first started like super fast, but after a year of using becoming so slow that it's like impossible to slow. And they didn't know that SSD drives should never be defragmented. So people used to regular drives, and they knew to increase the speed they need to defragment. But SSD should never be defragmented because this data should never be organized. And since we already start talking about FAT and how FAT systems work, we're going to move forward talking about file systems in Windows. But before that, if you have any questions regarding two different types of storage. Nope? Nobody have any questions? Okay. We're going to do no. That's not what I wanted to do. Don't save. So we start talking about FAT and file allocation table. So we have our file allocation. Here is a pointer. And here we have file. And we have our platters or our SSD drive. It doesn't matter with NAND chips because when we have FAT system, we use file allocation table no matter what type of drive or what type of storage device we use. So if it's thumb drive, by the way, thumb drive is the same technology that we use in SSD. It's just slower. And we have to realize that it doesn't matter what file system we use, it should be operate with both. So with FAT system and regular drives, it's sort of easy to understand that it points on specific location on the platter, right? It tells to the ARM to read from this disk, this track, this sector, right? So it gives direction like specifically where. But with SSD drive, where files constantly relocate, to have this pointer kind of not as easy as you might think. Is not gonna be not the same and as easy as with the regular drive, hard drive. However, it works exactly the same way. Because when we do defragmentation, we also relocate those files, so the pointer will be written to the new location. So with SSD drive, every time those bits of data moving, pointers will be just reassigned. So the pointer 1 would be first assigned to one part of the file, then it can be assigned to completely different, and then maybe it can be assigned as empty. So this data constantly just updating in FAT systems. Now let's talk about FAT systems in general. The first FAT system was used with, it's actually called FAT12. It was used with the first Windows systems. And it had a lot of limitations. We no longer use the FAT12. So the maximum size of the file was 32 megabit. That means you could not write any file that was larger than 32 megabits. Megabit. Then the volume size, and by volume size, I mean the number of clusters. It was 32 megabit as well. I just opened something that I didn't plan to open. Then came FAT16. FAT16 was used for quite some time. Even I remember when I was a kid, I was using FAT16 on my Windows 95 and Windows 98 systems. And it was using a maximum size of the file up to 2 gigabyte, which was tremendously increased the size of files you can write into the system, right? So finally you could put entire movie, not breaking this movie in chunks into the hard drive. But not to mention that the size of hard drives back in the days was so limited that you probably would not be able to put a movie there. So 2 gigabyte was already large enough, and the size of the volume 16 gigabyte. Then around Windows 98 they start using FAT32, and actually you can still format your SSD drive, your hard drive, or your thumb drive into FAT32. It just, you probably wouldn't because of the limitations. So it had limitation of the single file of 4 gigabyte. So you couldn't write any file that larger than 4 gigabyte. And the size of the volume can be maximum 32 gigabytes, which is, you probably understand, like ridiculously small. But compared to 32 megabyte, when it's basically like a diskette. I think diskette was formatted as FAT12, if I'm not wrong. And I think I'm not. I'm pretty sure that diskette was FAT12. So many of you don't know what is diskette, but if you check my screen right now, on the top left corner, you will see blue save button, blue square. That's a picture of this diskette. And now we use something that called exFAT. So originally, Microsoft created this file system for thumb drives, large thumb drives. So first thumb drives were really small, and using a file system that will be limited to 32 gigabytes was okay. I mean, I still remember time on 1 gigabyte thumb drive, it was like, wow, it's a lot. But now, right now, you can buy even terabyte thumb drive. And you would not be able to even format it in FAT32 because it's just not supporting its size, its volume. So you would use something that called exFAT. exFAT a lot similar to regular FAT. It's still using allocation tables, but the single file can be 46 gigabytes, and the maximum volume of the system can be, actually it's unlimited, but they put a limit, something like 16 gigabyte. So that's number that hard to even imagine right now. Well, we still can imagine it's a lot. So 1 terabyte, it's 1024 terabytes, and most of the computers right now have 1 terabyte hard drive. Sometimes even they don't have that, because if you have SSD drive, most likely you have something between 256 to 1 gig. Like Apple just got their MacBook Pro with 4 gigs, 4 terabytes of SSD drive, but it's new thing. I mean, it's extremely expensive, and my tablet went offline, so I need to charge it. Give me 1 second. Okay, fine. That's fine. We don't really need it anymore. I drew everything that I wanted to show you. So, next system that we need to talk about is called NTFS, New Technology File System. It's completely different from file system. It doesn't use allocation table. And instead, it's using master file table. It's also journaling file system, just like Linux using journaling file system, just like macOS using journaling file system. It uses just different type of allocation based on not location of individual bit of file on a drive, but based on a hierarchy, tree hierarchy of files and folders. And it supports file permissions, which is great add-on that FAT never had. So it's for security purposes, and it supports encryption. FAT32 didn't. And it also has metadata. You could not have metadata with FAT32. And if you check master file table, first 15 records of master file table will have only records that about this specific drive storage device, and you will go over details of this master file table header, that's what I would call it, or metadata of this drive in the book, or Arthur created video based on the book. But what you need to know, this first 15 records will provide you information about specific drive. And with that information, you will be able to locate different information in the drive easily if you will know how to read it in hex. And maximum file size with this file system would be 16 exabytes, which is as big as exFAT, which is great. It's really a lot of information for maximum size of the file. Permissions and encryptions. So you can assign, like in any journaling file system, to each individual file or folder or library permissions. Who is allowed to use it, when it's allowed to be used, who can write into this, for example, library of file, or who can read, or who can have full access to it. So you can encrypt and make it available for someone to be able to access and no one else. Or on opposite, you can just make it visible for everyone except one user. So that gives you a lot of flexibility with security. And here are some flaws. Linux doesn't support this file system. Mac doesn't support this file system. And current distros of Linux, if you connect thumb drive that formatted in NTFS, it will be able to see this drive, and most likely you will able to read information from this drive, but you will not be able to make any changes to write data or erase data on this drive. And my Windows computer is down. I was going to show you how to access information about your drive on the Windows system, but let's go over the labs again. So lab 5, the lab for this week, you will have to forensically format thumb drive. The reason I'm going over again because I didn't start recording when I was talking about this, and maybe some of you would like to go back and listen. So please try to find the thumb drive, the smallest possible volume. And by volume, I mean it should not be more than 1 gigabyte. And if you have some thumb drives in your house that you're not using, just use one of those. Just make sure that information that you have on this thumb drive, you no longer need it, because after forensically wiping this thumb drive, you will not be able to restore any of this information. And I'm absolutely serious, because don't forget that thumb drives, it's also non-technology.
They'll still be able to be used after we wipe them, correct?
Yes,
Okay.
you will not destroy them. You will destroy information. So you can choose any tool to do forensic wipe. So you have a lot of different options. Do your own research. I'm not asking you to use few different tools. You need to choose one, but you have to create a video tutorial walkthrough. How did you forensically erase this thumb drive? And you have to explain why we need it and how this process worked. So I'm gonna finish recording, and if you have questions, I would be happy to answer them.